Good morning, everyone. Good morning, good afternoon, good evening, wherever you are watching us today. It is a great honor and a pleasure to chair the first session of the second day of the 13th Annual International Workshop on Advanced Materials. So today we have great talks, and I hope you will stick with us and enjoy the talks. The first talk is from India, and it's from the same group as a colleague of us, Sainer Rao, that he couldn't make it here. So Professor Eswaramoorthy Muthusamy, I hope I did right, is giving the first talk, and he is for Jawaharlal Nehru Center of Advanced Scientific Research from Bangalore, India, and he will tell us about catalytic conversion of propane to propylene, strategies and challenges. So the floor is yours.
Thank you for a kind introduction. It's a great honor for me to give this talk in front of this august audience. Before I begin my talk, I would like to express my sincere thanks and gratitude to His Highness Sheikh Saud bin Sagar Al Husaymi for the generous support and excellent hospitality. I also thank Professor Cheetham and Professor Rao for the invitation to give this talk in this 13th annual workshop in advanced materials, on advanced materials. So today I will be giving a talk on catalytic conversion of propane to propylene, the challenges and opportunities. And propylene is an important chemical, so find applications in many chemical industries. Its intermediates, in fact, the derivatives of propylene has application in paint and plastics and automobile industries. In fact, the major use of propylene goes to polypropylene industry. Almost 60% of the propylene produced is used in the polypropylene industries. And the last 2 decades seen 2 times or huge increase in the demand for propylene, and there is a huge lot of demand for the supply and the demand for the propylene in industries. And you can see the global propylene market is projected to reach $137 billion by 2027. In fact, the rising demand for commercial vehicles and rapid growth for e-commerce, which again demands for packaging, and the continuous growth of construction sectors all are contributing to that increasing demand of propylene. And the conventional process to produce propylene is from the steam cracking and the catalytic cracking, and is mainly used to prepare that ethylene, which is an important feedstock in the polyethylene industries. In fact, the propylene is a byproduct in ethylene synthesis. And 85% of the market share of propylene comes from this catalytic and steam cracking. But recent advances, the advent of shale gas, which is driving this ethylene industries away from the heavier feedstock. In fact, if you use that gas oil or naphtha and steam cracking, you would see that propylene to ethylene ratio is almost like a 40% to 50% of propylene comes as a byproduct. And so in future, on-purpose propylene production from propane will play an important role. And if you look at it, the ExxonMobil invested around $20 billion in the shale gas production. And the shale gas is a natural gas that is trapped within the shale formations. And the shales are fine-grained sedimentary rocks, rich resources of petroleum and natural gas. So with this huge investment in the shale gas production, there's a huge demand for on-site production of propylene from this propane dehydrogenation. So we'll be moving away from the heavier feedstock, the steam cracking and catalytic cracking, and this makes that important process in coming years. And in fact, the shale gas is changing the propylene production. So many petrochemical companies announces that production of propylene from the propane dehydrogenation, on-site production of propane, dehydrogenation. And Dow and C3 Petrochemicals and many petroleum industries announces the production of propylene from this dehydrogenation of propane. In fact, in 2010, Petrologistics started the world's largest PDH plant, so making propylene directly rather than that a small byproduct of cracking from gasoline. And even in India, the first PDH plant is going to operate in 2024. The GAIL India has selected that Lummus technology is a cut-off-in process, which they are expecting that it will start operations by 2024, nearly $1.2 billion project. So there's a lot of demand for that on-site production of propylene. So there are two important processes, the on-purpose propylene production. So one is non-oxidative dehydrogenation. That's a PDH process. Other one is oxidative dehydrogenation of propane. Both requires catalysts. And there are many catalysts involved, the metal-based catalysts, metal oxide-based catalysts, and even other formulations. Even there are supports, many supports, metal placed on this oxide support, carbon support, carbide support. So many supports are used in this all research, most of them. Even the metal oxide, chromium oxide, vanadium oxide-based oxides are used extensively. But industry, for the catalytic non-oxidative dehydrogenation, there are two important processes, the cut-off-in and oleflux. So the cut-off-in uses the chromia supported on alumina, which is promoted by that 1 or 2% of alkali metal, sodium or potassium. And the other one, oleflux, this is like a platinum and tin on alumina support, which is again promoted by that alkali metal. This is by the UOP technology, and the other one is that ABBS Lummus technology. So these are another one of the star process that is not this level of popular. And see this the important this is a non-oxidative dehydrogenation endothermic process. So you can see that enthalpy is around 124 kilojoule per mole. So that means you have to operate this reaction at a very high temperature, and also you have to get a good efficiency. It is controlled by thermodynamic equilibrium, and a good efficiency you have to operate at a little low pressure of propane, low concentration of propane, so to improve its productivity. And it's operating at high temperature. Naturally, the cracking becomes significant. It leads to that many undesirable byproducts. In fact, coking is a major problem. It causes rapid catalyst deactivation. And in fact, in case of platinum catalyst, every 12 minutes of dehydrogenation, you have to regenerate the catalyst for a few minutes again. At present, there are 14 plants operating globally, more than 14 plants. Almost 14% of the market share for propane production comes from this methods, PDH. And as I said, that almost 85% of propylene comes from the petrochemical steam cracking. And for platinum and chromia catalyst, this is an activation process. The propane, that first step, that hydrogen removal from platinum surface. And chromia, this is a chromium 3+ was a major component where the initial stage of hydrogen removal and goes on. And the big problem in the platinum-based catalyst, in fact, platinum is more preferred than the chromia, not only for the environmental things, it's a high selectivity and activity compared to the other process. But the big problem is said that coke formation and the sintering and even leaching of those phase separation and other things leads to that lesser activity. And no platinum catalyst can do almost like continuously for 24 hours in the industrial process. So they need a very quick, even chromia also, you need to regenerate very frequently, every few minutes once. And the first one, the activity, the CH activation, how good, depends upon the activity of the catalyst. And the selectivity, again, once the propylene formed, how fast it is desorbed from the active site plays a major role If it has a strong adsorption, then the deep hydrogenation and cracking leads to that coke formation. So the stability of the catalyst again depends upon the coke formation. So to avoid this kind of coke formation, people try to use a different methods of alloying the platinum particles. For example, a PT-PT ensemble, sorry. So this is a very active sites for over dehydrogenation and hydrogenolysis. So that leads to that cracking and then coke formation. So this, whatever you're seeing, this the 3 PT ensembles, they will, in this case, they have blocked with lead. So it blocks those active sites where it leads to that over dehydrogenation reaction. And then isolate the PT by the gallium. It's a PT gallium on alumina support this catalyst. So the PT1, the isolated PT, by allowing this for promising strategy here, they use, so the isolated PT by gallium, wherever PT3 ensemble, which is deactivating the catalyst by coke formation, they blocked those sites by using that lead. So thereby they were able to improve its activity and selectivity for a longer period of time. And in fact, they use the geometric as well as the electronic factors by introducing gallium. So they will make that sites electron rich. Thereby, once electron rich propylene formed, it can quickly dissolve and thereby improve its activity and selectivity. And in this case, the platinum is isolated by using the zinc. So the PT1 sites, which is showing a good activity, and it was showing almost like 600 minutes continuous activity without any loss. So conversion is more or less stable for nearly 10 hours. Whereas the one without things, normal platinum, it shows that decrease in activity with the time. So recently there's that Aliguzen group et al. They have reported by allying with the platinum with the tin. And even the platinum tin is a common strategy to improve its activity. The problem is that the phase separation is a big problem, and also they are not able to stop the formation of platinum ensembles. So here they use something like in situ molecular precursor where platinum and tin forms a molecular precursor. Then they loaded with the alumina support and giving this platinum tin at 2 nanometer, less than 2 nanometer particles, and showed that excellent stability and selectivity to propylene, almost greater than 19%. In fact, this non-oxidative dehydrogenation, the biggest problem, the thermodynamic limit, because you will be operating at a low concentration of propane feedstock. So they were able to show this improving beyond the thermodynamic limit operation. They reach almost 60% conversion, though it's at a longer run, it's still a challenging problem to keep that stability. So they were able to avoid the PT tin segregation and also the formation of tin oxide phase. So this is another way the people used that to introduce some acetic support on alumina, and thereby that whatever that nucleophilic olefinic things formed can be moved to that acidic support. Then the coke formation, the transfer of coke from that active sites to that support is another strategy people try to use it to improve the selectivity and the activity of the platinum. And even boron is shown that showing a very good promotion effect on the coke formation. When increasing the loading of boron, it shows that carbon to propylene ratio has come down. So it is a very beneficial effect in the decrease in that coke and thereby increase its activity. And even platinum containing the boron shows that longer time stability compared to that without boron introduction. And this are showing that when introduction of boron shows that they were able to monitor that in ammonia TPD, thereby they were able to see that if the boron reduces at strong acidic sites and thereby able to reduce that coke formation. But there are different arguments in this. Many literature comes with a different argument on how this reduction of coke happens when introducing boron. And this way, here they were able to show that the boron platinum again shows a good conversion and selectivity with respect to that in presence of boron. So all again we have to depend on the platinum, which is a noble metals. Again, long-term stability is not there, and even the industry process they will mix with a little bit of hydrogen. Thereby they can reduce the coke formation, and saturated olefinic things can be converted into saturated and can leave the surface. So there are a lot of challenges in the platinum. So people are looking for that non-noble metal catalyst, and even the carbon people try to see that whether there's a good catalyst for the dehydrogenation process. Though there are reports which shows that functionalized carbon shows a good activity for the styrene dehydrogenation, oxidative dehydrogenation, but no report on this kind of non-oxidative dehydrogenation process. The big problem is that since it has to operate at a higher temperature, the stability is the compromising factor. When you go for higher temperature, decomposition of carbon is a challenging phenomenon. On the other hand, the BCN, which we have prepared in a So this is another work where people try to use that zirconium oxide in a way controlled, isolated zirconium oxide shows the higher activity for propane dehydrogenation, non-oxidative way. And even recently they have a report where the zinc oxide, which is isolated zinc oxide species, which is, in fact, the interesting way they prepared it, they use a zeolite type of support and then separated, put a quartz wool and then zinc oxide, then pass a hydrogen, and thereby that whatever that zinc, some of them reduces zinc, goes and deposits on silanol groups available on the silica support. So it forms SiO-ZN type of species. So that shows that a very high activity for propane dehydrogenation. So they are even able to show that the calculation to single isolated zinc shows that less activation energy barrier compared to that two-centered zinc species. But there are a lot of work on this direction going on. So we have made that BCN, which is very stable at very high temperature. Even in presence of oxygen, it decomposes only at 600 degree and above. And thereby we can use it for this kind of dehydrogenation of alkane molecule. So we prepared using this boric acid diethylamide mixture using this carbon, high surface area carbon, and that shows that almost like a 2,000 meters square per gram, the surface area. And it's a lot of defects, which is shown in this XRD. You can see that the very broad peaks. And then the stability, you can, even in oxygen, it is stable at 600 degrees centigrade. And the IR also shows that the presence of BN and C and CV bonds, which is standard characterization used for this. And the catalyst is testing, which we have packed this catalyst in a reactor and then pass it propane and analyze the gases with the GC and MS route. And here you can see that we have compared the activity with respect to temperature with the blank without any catalyst, boron nitride, which is again shows no activity, whereas the carbon, which shows a higher activity at 650 degrees centigrade, and BCN, though it's less activity. But however, the carbon, the stability of the carbon for longer run is not good. And if you look at the carbon, this is a reaction carried out at 650 degrees centigrade. You can see this conversion of the carbon goes drastically down with respect to time. Even with 100 hours, it's going down very drastically. Whereas in this case, the conversions were here and stable even at 100 hours without much loss in activity and very high selectivity for olefins, propylene and ethylene products. And the coke deposition rate, if you look at it, the carbon it's almost like a 12.8 milligram per gram of catalyst per hour, whereas in the BCN it shows that 1.25 milligrams, so almost like a 1 order of magnitude decrease in that coke formation. And even if you carry out at 600 degrees centigrade, you are able to stabilize this activity more than 400 hours. So without any loss in activity, and also selectivity compared to that carbon-based material. So, and even that characterization of this catalyst, fresh and spent catalyst, did not show any big difference in this graphitic regions, and as well as its kind of Raman spectra, and even the imaging all shows that almost equal composition distribution of BCN. And look into the functional moieties in the BCN. We have carried out that ammonia TPD, where that carbon shows that there is no signal in this range from room temperature to 400 degrees. On the other hand, in the case of BCN, you see that that BOH group, which is associated with that ammonia adsorption, desorption. So the BCN fresh shows at very high BOH groups compared to that BCN 600, treated at 600 degrees for 100 hours. It shows that less amount of BOH group. But we are not clear whether these are the active sites for this kind of reaction, and even the functional group, which you can see the carbon gas, there are a lot of carbonyl and phenol gas to functional group, which on spent catalyst has come down drastically, very much reduced, whereas in the case of BCN, there is no desorption, and it means if you use that active carbon there, you will lose that active sites, which probably that carbonyl kind of active sites, which will known for the anthraquinone process, where the quinone dehydrogenation, hydrogenation go to hydroquinone and then dehydrogenation. So hydrogen peroxides in this anthraquinone process. Such kind of activity probably happening in carbon. But the problem is that at high temperature, those functional groups are, even though it shows activity, they are removed, so the activity gone down. Whereas in the BCN, we didn't see such loss in activity because these groups, whatever are available, they are not reduced, retained there. And again, this is a coke deactivation parameter. So one of the important parameters in the industrial things. You can see that catalyst, the BCN at 600 degrees is a very, very low KD value. And the coke formation rate is also very, very low, 0.06 compared to other carbon, even in many other industrial catalysts. So this table shows that the deactivation rate of many of these catalysts, metal-based molybdenum, iron, chromium, whereas they all, ideally you need this very formation rate high and deactivation rate is low. So if you look at this map, you can see that BCN stands out, very high rate, formation rate with very, very low activation, deactivation rate. So it shows that very excellent performance, and that mechanistic aspect which we are looking at it, how these things shows that higher activity. And then coming back to the other process in the in situ on-site production of propane to propylene is oxidative dehydrogenation. There is no industrial process right now because the big issue is here in the oxidative dehydrogenation. The combustion of a hydrocarbon to CO2 is a major problem, but nevertheless it is thermodynamically unrestricted. You can operate at a much lower temperature, and also is expected to see that energy savings almost like 45%, and thereby you can minimize the coke deposition and long-term stability of the catalyst. So, but the problem is the side and parallel reactions limit the propylene selectivity. And if you look at it, the CC bond dissociation energy of propane, this one, and CH bond dissociation energy in the propylene, these are more or less a 360 and 370 kilojoule per mole, whereas the CH dissociation energy of propane, which is 420. So that shows that once propylene formed, the other cracking reaction dominates in most of the cases, and then it undergoes combustion to completely into CO2 and water. So there's a big challenge, and the mechanistic way the people showed for in case of ethyl benzene dehydrogenation, the formation of this the quinone type of groups on adsorption of ethyl benzene undergo the hydrogen abstraction and forms it diol, and then further it reacts with the oxygen, goes back to that quinone. So this was the like a Mars Van Grieven kind of mechanisms, which is known in vanadium oxide-based catalyst. So people show this could be that probable mechanism for this oxidative dehydrogenation by carbon, though vanadium-based catalysts are used, but this recently got a lot of attention. Many people try to look at it. Even the carbon nanotube for N-butane hydrogenation, same such kind of mechanism is proposed. But however, the presence of any ester type of linkages are highly nucleophilic oxygen, which leads to that combustion of this olefin, leading to that CO2 and water. So the complete combustion, depending upon the functional groups available on carbon nanotube, they were able to see that variation in the product selectivity. And when they introduce the phosphate, which is electron deficient, so they can withdraw that electron-rich moiety, thereby it improves its selectivity. So, and even the introduction of heteroatoms, so increase the selectivity of those oxidative dehydrogenation reaction. For example, this boron introduction here, they show that the decomposition of this monitored at different temperature in mass spec show that in mass spec shows that the decomposition of carbon in presence of boron that moves to that higher temperature, and thereby it retains its stability for a longer period of time. And even the boron doped this carbon nanotube shows that longer period of activity and also the selectivity long period at 673 Kelvin. And this time the boron nitride catalyst they have reported where the Hermann group, they found that people thought that it may not be active at all, but they showed that it's very interestingly, it shows a 14% propane conversion, and with a selectivity of around 80% propane as a desired alkene. But if you raise the temperature, then the complete decomposition is a major problem. And they were able to achieve up to this 14%. It's a very low conversion. Boron nitride shows at very high selectivity for propylene. And the mechanism is similar to that carbon, the quinone kind of reaction, the keto groups. And here BOO, the ester kind of linkages. So the propane, the chemical, the hydrogen adsorption happens at this OO center, and then further the breaking of this chain and leads to that CO boron bond, and then this further CH continuous abstraction leading to this type of, you can see this one, the CH again further absorption leads to this OO minus. And in presence of oxygen, you can regenerate that whole cycle. So that is like a similar to oxidative dehydrogenation in the carbon nanotube. But later they also show that this kind of linkages may not be effective for longer run. So we have carried out with the BN, but at a high surface area BN, which is prepared by using that kind of nitrogen source and then boron, boric acid, and cyanamide precursor, and which is giving a good activity, which is around 500 degrees centigrade, have good conversion around 40%, and with selectivity of around 50%, which is reasonably high compared to that many other catalysts reported. And the thing is that we have used this boron nitride from kind of boron and nitrogen precursors, which shows that a very disordered structure, thereby the high surface area and stability for that even at 800 degrees, more stable in presence of oxygen, and that leads to that very high yield. And looking at with respect to surface area, we were able to see that very good yield going from up to 38% of propane and ethylene was obtained. And varying the surface area, the conversion, keeping conversion at 53, we were able to achieve up to 38% yield. And interestingly, there is a decrease in activity. If you can see here, at above up to 500 degrees, there's not much conversion, but above 500 degrees, it shows that good activity. But the problem is that selectivity comes down when you increase the temperature. And you'll see that the activity we are able to maintain at that temperature And you can see that after 6 hours, you're able to retain this activity at 550 degrees centigrade. And then increasing a time, you see that sharp decrease in the conversion, whereas the selectivity increases. So that problem is due to the formation of oxide species. You'll see that BN and time on steam steady spin catalyst shows that formation, the signature for NBO stitching bonds, and then which reduces the activity, and then you treat this with the ammonia, then you are able to get back to that activity. So by treating this ammonia, you are able to bring back to the original structure. So this shows that this a BN bond is a more active for this reaction. In fact, when you are using the spent catalyst shows almost like a similar characterization of the fresh catalyst after 50 hours or 100 hours time. And then even the XPS analysis shows that as a fresh catalyst, the BN bond, and there is very limited BNO binding energy associated with this one. On the case of a spin catalyst, you can see the huge peak associated with the BO stitching, the binding energy for PO, and also BN for boron binding energy. And this one, after regeneration, you are able to get back to that original BN catalyst. So this shows that it's not like that BO kind of bond which is shown in that Herman's paper. It will be that BN kind of bonds plays a major role. In fact, when we are carrying out the whole reaction in presence of ammonia, so we were able to retain the activity continuously more than 100 hours without any loss in activity. So it's clearly indicated. In fact, if you look at that spin catalyst and the fresh catalyst, there is no change in that IR spectrum, indicating that the catalytic sites may not be BOOB type of sites. It will be related to the BN stitching, BN bond later. So we do not know exact, so we have to do some calculation to look at it exact energy and other things. On the other hand, when we treat with the commercial HBN catalyst, and there is no significant activity, and then if you look at the conversion, it goes up to 550, you can see even 40 degree, but there is no selectivity for propane, ethylene. And this conventional, the commercial HBN catalyst, the surface area found to be around 48 meters square, but no activity you are able to see that with respect to HBN. And this is a big challenge. In fact, recently there has one paper came with that isolation of boron in zeolite for the oxidative dehydrogenation of propane. And here the isolated boron with the BOH, SiOH kind of hydrogen bonding structure. In borosilicate zeolites, it acts as an active center which enables the activation of oxygen and carbon hydrogen bond to catalyze that oxidative dehydrogenation of propane. So there are many studies that the major strategy is that only isolation of the active sites and avoid that dehydrogenation, deep dehydrogenation reactions. And when in the case of oxidative dehydrogenation, how to prevent the complete oxidation. So that's a big challenge in not only in propane dehydrogenation, many of the functionalization of hydrocarbon using the oxygen. That's one of the biggest challenge. And to conclude that in this field, the platinum still remains the most active catalyst for propane dehydrogenation, but the cost and stability are the major disadvantages of this catalyst. And still commercial the industries uses only platinum and chromium-based catalyst in propane dehydrogenation. And the isolation of active sites either by geometric, increase in the electron density by doping, so increases the PDH activity of platinum catalyst. Such effects are also observed even in a zinc and boron-based catalysts. And metal-free BN and BCN catalyst shows extremely stable catalytic activity for ODH and oxidative dehydrogenation as well as PDH, just non-oxidative dehydrogenation respectively. So the presence of BOH, CO groups in BCN expected to play the role as an active sites in the BDH reaction, but still a lot of work to do what type of nature of the active sites. So with this, I would like to conclude. I would like to acknowledge the student who worked, the Momin Ahmed, and also Dr. Piyush Chaturbedi, who is now postdoc in Cambridge University, and the JNC ASR and DST for the funding and acknowledge the Sheikh Sakar Career Award Fellowship. So thank you. Now my time.
Thank you, Professor Eswaramoorthy, for a great talk. I'm sure that we have plenty of questions. We have a lot of catalyst experts in the room. And also, I encourage the audience following us online to write their questions on the chat box. Any questions? I just checked online. There is no questions so far. Any questions from the room? Yes, Professor Ben. Let's get the microphone so the audience can hear from the other side.
Thank you very much. I enjoyed your lecture very much.
Thank you.
I had a question about, the activity. You say you have a very high active system also with the boron. What about the temperatures where we run these reactions? Because usually you need high temperature, but you did not mention too much the temperature. Can we reduce the temperature also quite drastically?
Yeah, in the oxidative dehydrogenation, you can reduce the temperature significantly. But in non-oxidative dehydrogenation, you need to go for higher temperature. Though that's still a problem, but since we are introducing boron in that carbon matrix, is able to stabilize that matrix for a very even at high temperature. That's the biggest advantage.
But from the energy perspective, there's of course high catalytic activity because we would also like to reduce a bit,
Yes.
and to get a better pathway at lower temperature.
Yeah, in case of BCN, which is that we are operating almost at industry operates around 700 degrees centigrade. We have done at 650 or even at a little lower temperature, 600 degrees centigrade, which shows that though we will not be able to give the higher conversion, but a very good stability and a long run without.
So now I challenge you, Mother Nature does this at room temperature.
Yes,
Can we ever do this kind of processes at lower temperatures to make more active? What do you think? What is the future?
Yeah, that's in fact, that's the biggest thing where you can use it like individual complex or something like the way the mimicking that what nature does. It's a bit challenging, of course.
I know.
I can understand.
I can.
There are certain problems like noble problems, which is ever learning.
Thank you very much.
Another question here,
great
Professor Cheetham. Right here.
Yes, and thank you very much, Eshwar. A really interesting talk. I was right at the end. You mentioned the work on the borosilicate zeolite.
Yes, which you are
and
familiar.
There's a long history to borosilicate zeolites for xylene isomerization, and there was a litigation 20 years ago in the federal court in Delaware, and what became clear, and I was one of the expert witnesses, is that boron in aluminosilicate zeolites is not very stable. And because boron's so much smaller than silicon and aluminum, and it's not practical to keep it in the lattice. I wondered if the work in science actually addressed that issue.
Yeah, here they didn't put it in the kind of framework. The boron is not replacing the silicon or something. What they have done is the boron interacts with the silanol bond, SiOH, where there are links with boron. So SiOB bond, that plays that activity role. So it's not like in the framework where like isomorphic substitution, no.
Yeah.
So
With your BN catalysts,
yeah.
and I might have missed it because I had to pop out to do an interview.
Okay.
But did you look at different kind of polymorphs of BN, including things like boron nitride nanotubes and so
So
on?
this is boron nitride nanotube. People have reported as a very well characterized boron nitride. So what our boron nitride is a bit more amorphous. There are a lot of defects in that in the process. So a little bit you can see the XRD. So there are a lot of defect sites. BN sites, I feel that it may be active. We do not know how that abstract of hydrogen, which is different from what the Herman's group, they were claiming that BOH like a one-dimensional structure. So here, when the activity goes down, but you treat with the ammonia, then comes back. And in fact, if you do the reaction in presence of ammonia, you are able to retain the activity for long times. So that's the active sites are different here, I feel.
Yeah.
Thank you.
Thank you. I have.
And this is not HBN, sorry.
Yeah.
The defect, sorry.
I have a quick question, maybe philosophical. So normally you mentioned at the beginning that you need high purity propane in order to use it for polypropylene, for example.
Yeah.
But what is your purity of the propane that you get at the end? And is it actually the required 99.9 that you need for propylene? And if that's not the case, are you exploring any ways to do separation to make it pure?
Yes. So ideally, you would like to have 100% propylene.
99.9 is
Yes. Okay.
the
But
99.5 is
yeah,
good for
above
other
90,
things.
yes, still it's a possible you can make it.
So in
with
your
the
case, what is the
separation.
purity of the propane you get?
It's above 90%. It's only
About 90%.
propylene and ethylene we are getting.
Yeah, exactly. So are you planning to
Separation.
separate those?
Yeah. So that we need to take it up next process because we need to see that what are the economically viable separation process, either membrane
So you're
route
still
or
gonna
anything.
need the separation.
Maybe some kind of MOF type of things.
So you're
it
gonna
could
need
be.
separation.
Yes, sure, sure.
So with that, please join me to thank Professor Eswaramoorthy for his talk.
Thank you.